They don't want to do anything. They just want to be a YouTube streamer or Twitch streamer or not even just stream video games. Just be popular on YouTube and like holy smokes. You gotta have a backup plan, I guess.
Yeah.
All right, so kind of switching gears, sort of new concept, which is external flow or external drag. We're going to define drag. We're going to define surface drag and boundary layers. Get into pressure drag, and really that's all analyzing external flow. So we have external flow to cover, and then after we're done with this, probably next Thursday, I'll probably do like a mini project individually where you design probably your like a wing, and we'll stick in a wind tunnel. So I'll have you design it, and we'll 3D print it. Pretty small, nothing too big.
So we'll do that in one class.
Yeah,
Well, we'll start.
yeah. So it'll be like after this because we need to know this stuff, and then I want to do some hands-on stuff. Then I can give you the final project, which you can start, and that's going to be profiling the wind tunnel. So getting contour maps, and you can work in groups of 2 for that, and then other things with the wind tunnel. Okay, that it'd be pretty cool to do. Okay, we got Navier-Stokes equations to cover and compressible flow. And then Chris wanted to, and that's good, it'd be good for you guys, I'm going to do probably a couple lectures on prop design, which I think would be a good idea. And then I still want to do a lab at Clarkson. So we still have a few weeks to go, stuff to cover, but I think it's going to be doable. So, hello, Will.
There's no traffic.
Are you red because you're late or red because it's cold out?
Bridge traffic.
Oh, man.
Did you hear they had to reconstruct it already? It's already broken down.
Only when
They took away your landing zone, did they?
They actually are working on it right now.
Are they again? They're working on
It's just like one side.
Oh.
Away from school though. It wouldn't stop me.
it? You just
Well, you can
drive
get a
right
helicopter,
through.
Then you can just fly right there.
Yeah. I hit a couple cars on the way.
So that's kind of the plan for the rest of the semester. External flow, compressible flow, Navier-Stokes, some hands-on stuff, prop design. So, all right, so let's get, I have a PowerPoint that I'll go through and then we'll take some notes. Yep. Is that what I had? Oh. So just a quick idea, and you've probably seen this before. Why does it fly farther?
Farther than what?
The dimples.
Yeah, than a regular
Oh,
spear ball.
Oh, because there's the
Eyes
The
reduced,
dimples.
never hit.
Yes, the dimples reduce drag. And what does that really mean by reducing drag?
It maintains its acceleration.
It flashes the air better.
Oh, okay. Okay. What about if I drew the streamlines?
I was gonna
If this ball was moving this way?
There's no stagnation. Well, there's not like many stagnation points.
There's less thickness behind it. There's less.
Ah, okay. You're getting on the right direction. The flow, when the dimples comes back closer, okay, it doesn't create this big wake back here. It creates a smaller wake with the dimples, okay? And we'll go through some of that, all right? Here's just kind of a why. Here's a smooth ball. You get this big wake. Here's this golf ball, which has dimples, and you get this smaller wake. Okay, you still get drag, but it's actually reduced because it creates turbulence back here, and it starts spinning. And it kind of, think of it as like arms. They're kind of grabbing that and bringing it back down. Same with here. They're grabbing this and kind of bringing it towards the center. Okay, that's what the circulations actually help do. So that's why. It's pretty cool. I think Mythbusters actually did it. They did dimples on a car and tested it. I don't know the results. Did you know the results?
Positive
Did it work?
results.
It was good.
Plausible.
So plausible. Okay, good. So what we're going to start talking about is flow over bodies. So complete entire flow. All right, like previous, we've been looking at like a hose that we know the diameter shooting out and maybe hitting something where we did linear momentum. This is now the flow is just so much larger and it goes over the object. Okay, so we're going to look at airplanes. We can kind of look at turbines and different kind of shapes here. Sailboats, submarines, planes, we'll start now talking about, like, okay, you have eyes on birds, you have eyes on whales, and their eyes are in a certain location, like I think I mentioned this before, where it doesn't get blurry. And we'll talk about all that stuff, okay? This is some of the stuff that hopefully I'll hear within this week or next week about the campus enhancement to build those small wind tunnels. This is something we can now see as external flow, which is a flow visualization that you were learned about using smoke or whatever. Okay, so now you'll be able to understand where drag comes in and how to improve it. Okay. And I think, and I should check, I think Mr. Baldwin actually might have one of these. So it'd be pretty cool to take that, maybe do that for Engineers Week if we do have one. Yeah, if he has one, that'd be sweet to do next semester and show kids. Take it right out here and block a section out in the driveway, have some lights on it, shoot it across. That'd be cool. Okay, don't worry about this. This is for you for just later if you want to read it. Let's look at the top left. This right here is very similar to when you stick your hand out a car window and it's flat like this. Okay, you have less surface area hitting the wind, but you have more of your surface, like this, touching. So this right here is surface drag. Okay, a lot of the top part is touching the air. Okay, where this one right here is spun around. Now you have this big frontal area where the wind is blowing, hitting it. This is what they call pressure drag. Okay? You still have, if you notice, you still get a little bit of pressure drag in here. You still get a little bit of surface drag here. But 95% of this is pressure. 95% of this is surface drag. However, looking at a sphere, that's almost 50-50. It has both pressure and surface drag. Okay? And that's kind of how they classify types of drag: pressure, surface, and the sphere. And this is what I want to actually, I'm going to start working on and designing, is I'm going to design one of these, print it with holes, stick it in the wind tunnel, and actually get measurements around the sphere. Compare that, that's probably going to be your project too. Compare that to the experimental values we get in the wind tunnel. So I'll probably give you that project here in the next few weeks so you can start thinking about it. So that project will consist of really the wind tunnel, doing a contour map of different slices, taking one of these, sticking it in there, and actually measuring and comparing. And then if I'll give you that and maybe some other projects if you want to do that too. Okay, if you want to do something else. All right. And we're going to get into more detail on these coming up, but I'll go through some of this and then we'll get back into notes. So here we talked about this as just a regular tennis ball. You got wake regions, but someone actually drew up the Enterprise, put that in ANSYS, and did a computational fluid dynamics. Okay. No, I don't think they did. Can't read that. They might have. I have to check to see their results. They could have, but I don't know how accurate that would be in ANSYS or Inventor. I'm not sure. But this is some of the stuff that I want you to start doing. So in this next homework that I just got posted, you're going to pick a tutorial. And I give you a list of them. You can either do it in ANSYS or Inventor. Doesn't matter to me. And either you could do like something like this where you put an object in a wind tunnel, or more of like homework 1 where it was a pipe flow. Okay, so it's up to you what you want to do for that. Just to get you more familiarized with that software and what CFD can actually do for you. Do I want to go? Sure, I can talk about this and we'll get back to it. Any questions so far? I haven't given you any equations yet. We'll get to those, but just more of a general idea of how things work. All right, so let's look at this top picture, and we're gonna probably get back to this, but anytime, like if I'm walking or moving in air, moving in any fluid, okay, there's always gonna be a boundary layer, meaning that the liquid sticks to my surface. Okay, so as I'm walking, it's like past my arm here, the velocity of the air right here on my skin is 0 because it's sticking to me. Okay, because my arm is like not moving back and forth. Okay, away from that, okay, the air is moving at whatever speed that I'm moving at. Okay, so if an airplane's flying through the air, it has a boundary layer, and it grows as it goes past in the back end of the airplane. Okay, and I'll show you, and we'll draw some sketches here. But there's going to be a certain point where this fluid goes around and basically it sticks to the surface, but it gets to a certain point in this case where it can't really stick anymore. Okay, and it becomes unattached or detached from the surface. Think about when you're running really fast down the hallway, you're trying to make a curve, okay, or a bend. You don't quite make it if you're running too fast. But if you're going slow enough, you can. This is exactly what's happening here. So the flow is going around here, gets to a certain point, can't make this bend because it's now a sharp bend, and boom, it becomes detached. Okay, and that's where you get those wake regions. And we'll talk more about this. This is what they call flow separation. And that's the reason why we get drag. Okay, if we didn't have these flow separations and everything came back to normal, then there would be no drag. We can slide through everything and not have to worry about anything. Okay, but there becomes a point where it doesn't stick anymore, just because it can't make that bend. Some of that flow can't, and it becomes detached. Okay, and it depends on the type of flow. So if it's laminar, turbulent, or in this case, if you notice this dotted line here, that's an ideal case where there's no drag at all. Okay, the flow comes right back to where it should actually start. So let's stop here and let's take some notes now so you can understand where drag comes from and some equations. Okay, so drag. The drag force for us is 1/2 rho v squared CD times A. And this is actually Reynolds number much greater than 1. Okay? Much, much greater, yeah. Do you remember what, and we talked about this before, what the Reynolds number equation was and what two forces it related? It's rho b L, sure, some characteristic length, over mu. Okay? And this compared what is velocity in terms of energy? Kinetic or inertia, so it's moving, over mu, which is a viscosity, which is friction forces. So it's inertia over your friction force. That's kind of what it relates. So if we have, for us, large Reynolds number has a lot of inertia. We have a lot of mass, and as we move with acceleration, that term is huge compared to the viscous force in air. If we were moving in like honey, that equation is no longer valid because that viscous force is now much greater, okay? Or if you have a steel ball dropped in oil, there's a different equation. And that equation, if you want to write it down, I don't have it in my notes, but I remember 3 pi mu V times D, actually over CC, and I'll talk about what that is.
And that's for oil?
This is when the Reynolds number is less than 1. Yep.
So like how many orders of magnitude are we talking for like much?
Like this, actually, we could probably just do less than 1. Yep. And the Reynolds number, you're going to see is probably usually always over 100 1,000.
Okay.
Yep. These are like around 1 or lower, significantly lower. Okay. So this drag force is primarily due to viscous. This, if you notice, is due to inertia or kinetic energy, the top one. So 3 pi mu velocity times diameter usually, or some sort of characteristic diameter. So if you take a pollen particle, all right, they're really small, they're floating in air around, or dust particle, if you open your window, you ever see that with the dust flying through the sun? Those use that because they're really, really small, really light, but going through air, that force, you'd have to use that, okay? Now the 3 pi mu VD makes sense. This CC is what they call a Cunningham correction factor. That is only actually used when the particles are about the same size or much smaller than the gas particles. Okay, really, really small. I mean, you'd have to, I don't even think they can see that with a microscope. Okay, but they know they're there. Okay? Because if you have gas particles, which are this size, for example, and you have like a particle that's smaller than that, this one's going to bounce this one around and hit it, right? And bounce it around. That's why you have to include that. Because now you have that factoring, which is pretty crazy, right? It's like us bouncing around really small balls, okay? We're kind of pushing around these gas particles, and you have to include that. For you guys, I wouldn't worry too much about that. It's going to be this one right here, okay? I wanted to let you know that there's actually 2 different types of drag. This one you actually used, you remember the falling ball viscometer? That's the equation you used in there, because that you can find the viscosity of the fluid, okay? When you did dynamics, or some of you in dynamics now, you have, or even physics, here's a ball, and it gets launched off at some initial velocity. Shoots in air. Do we ever use drag? No, you neglect it. Why? Because it's pretty hard to actually find the velocity squared, because it's nonlinear. But you now know, say we have a ball, and say it's falling. And I think on your homework problem, and I'll get to this, you have a ball that I want you to do. You're going to drop off from a certain height. You could do and test this if you want. But I want you to plot the terminal velocity, or velocity as a function of time, and you'll actually reach terminal velocity. So if you have a ball that's falling, so it's going down this way, you have weight, and you also now have drag, okay? So if you sum these forces in the y equals MAY. And downward is positive. So you have W minus FD equals MAY. Could someone tell me the initial acceleration?
Gravity.
Well, you're a little above 0, right? Because we drop it. What's going to happen to this acceleration? It's going to start increasing until it approaches, which is gravity, and no longer accelerates anymore. Okay, because these two are reaching each other. They've now, this force equals that force, so this is no longer accelerating anymore. That's where terminal velocity is reached. Okay. So a lot of students, and I hope this makes sense. This right here, Newton's second law, is used to find acceleration. If we have drag in there, this isn't 9.81. If you just had weight, like we do in physics, so if we just had weight and we sum the forces, this was mg equals ma. What is the acceleration? Gravity. This is what you've always been taught, but it's technically not right because you have a drag force in there that we always neglect. Okay? Which, these actually give you pretty close numbers. If you've done actually experiments, they're pretty close. That's why we teach you that. Okay. This is the more correct. Actually, this isn't correct either. What are we missing in this one that you can assume neglected in here? We have a ball that's falling. We have gravity. We have drag. That's the drag.
The forward resistance.
What is that? What do you
It's
mean?
in the front, it's pushing the air out of the way.
That, and I'm going to talk about just that in a sec. That is actually the drag. Yep.
included in
That's
the drag.
included in the drag. Yes, and I'll talk about that in a second. Yep.
So we have lifting factor to the ball.
Okay, so you could have lift, so it could be spinning. Sure, I didn't think of that, but yeah, it could be spinning, or have some sort of. Sure, it could get lift, and it could help. Yep. But the surface area is included in the drag kind of thing. Buoyancy, yes, buoyancy. There is buoyancy, which we call B. There's lift. It could be spinning. All that has been neglected. But, yeah, go ahead, Devin.
So for skydiving, it's the same thing. It's just that
Exactly. This would be skydiving.
it's not dependent on the weight at all. Because
What isn't?
the terminal velocity.
We can find that out here in a second. Sure. We'll see it. So, there is buoyancy. There could be lift. But don't worry about lift, okay? Buoyancy, though, do you remember that equation?
Not off the top of my head.
I'm just doing it in fluid right now, so I know it. Density of the fluid, which is air, which is what? The standard conditions. 1.176, something like that. So that buoyancy force is so small that it doesn't do anything to the equations. But if you're dealing with small particles or small masses, like a steel ball and maybe liquid or water, you have to include it. Okay, there's certain situations when you have to include it. But that goes back to the Reynolds number. If the Reynolds number is large, you can ignore the buoyancy force too. Okay? Kind of throwing a lot of stuff at you. Questions?
Yeah.
Oh, this is density of the fluid. This is the volume submerged. So volume submerged. Well, in this case, it's completely submerged, so it'd be the total volume. Exactly. Yeah. If I told you don't do this in air, do it in water with a steel ball, you'd have to include buoyancy force. Because yeah, that's 1,000 now instead of 1.176. Yep. You see how you were taught basic stuff, and then now it's like, holy crap, there's a whole new set of forces that I didn't think about, and we get to this. So, questions? Kind of cool, right? Different things you can look at. Let's just write out this equation right here. So weight is mg minus 1/2 rho v squared cd times a equals m dv dt. I forgot to tell you, CD is the drag coefficient.
Is that usually given?
That's either given in tables or you find it experimentally. Yeah. And that's probably what I'll have you do for the project. Is stick different objects in there and actually find the drag coefficient.
You just put that in there and put force.
Yes. So you have to know, you have to have a force or drag measurement in order to get that. Yep. Those are all found experimentally. Yep. This is the, I believe it's the frontal area. It's not the surface area. It's the frontal area. And then acceleration, I just called dv dt. So what did I do, Ray? What did I just do here? I created not really a formula, but more of a, what do we in this equation here, what would we solve for?
Which equation?
This one boxed in red.
Some of that.
V. We're solving for V
Oh,
as a
okay.
function of time. So what is that called? A whole class dedicated on it. Differential equation. So this is a differential equation. What is the differential equation?
The equation with the function and its derivative.
Or higher derivatives, exactly. It's some sort of equation that you need to solve to get a functional equation, meaning you're going to get some equation down here that's a function of time. Okay? Can you classify this for me? First order. So let me write it in terms of what you probably have seen. Oh, that's a plus sign. Oh, man. And it's all divided by m equals g. So it's first order. Constant coefficients, meaning everything in front of your derivative or your velocity are all constants. So density is constant, CD is constant, A is constant, M. But it's non-homogeneous because it's equal to G, because G doesn't have a derivative or a velocity. And it's linear or nonlinear? Nonlinear, because it's power of 2. Now there is methods to solve this by hand, but it's tricky. You don't want to because it's a pain. Okay? What I'm going to show you, probably not this class, but next class, is how we use MATLAB or other codes to solve for this numerically. Okay? So that's one of the homework problems is going to have you solve this numerically. Then you could solve any differential equations the exact same way that I'm going to show you how to do it. So once you have that code built, you just pop in that equation there, and boom, you can solve it. So what is this going to look like if you plotted velocity versus time, just to get an idea? Yeah, it's going to start at 0, and eventually it's going to level off, right? And that's your terminal velocity. Assuming positive, right? Because if we're going downward, and you just pick your direction, right? So let's just see, yeah. Any questions so far before I dig a little deeper? So terminal velocity, we can find that right now. That's when the weight equals FD. Because if those two equal each other, the thing's not accelerating anymore. Okay? So the weight is mg. This is 1/2 rho v squared CD times A. And the velocity then becomes mg 2mg divided by rho CdA square root. So you have to know your area. Your depending on which way you're moving, right? Are you this way with the whole area this, or are you actually skydiving with that, like straight down? So you have very minimal area. But based on my analysis, it does depend on the mass, like this. And I think someone did this. Was this dynamics? Was it Tyler? It's the first, second week of dynamics class. He texted this out, and we got the right answer. We just had to figure out this and that. He did a calculation online. Yeah. And they actually matched. This equation matched to the equations or numbers he got from online. So, did you skydive before?
No.
Oh.
I didn't want to. My birthday this year.
Okay, so you can figure this out roughly. just to get an idea how fast you're actually going to go. Yep. Yep. Questions so far? Okay, now this is random, but this is good to help you with differential equations. And this may help too with you guys in mechatronics. I don't know. So here we have a spring mass system. This is a mass, this is K, and this is X. So this mass is attached to a spring, and it's on a frictionless surface. Don't worry about that. We're going to do a free body diagram on the mass. This is actually like vibrations, which I probably won't teach until the following semester or following year and a half. But that's all right. If I move this mass to the right a little bit, which way does the spring force want to go? That way, right? Call it Kx. Okay, Will, you all right?
Yeah.
Okay, I'm just making sure. You looked like you were thinking about something. Were you thinking about something?
Thinking about fluid.
Oh, okay. Fluids in the spring?
I think just about this class.
Okay.
And then
If I move this way, which way does inertia act? Opposite way too. That's ma. Remember Newton's second law, sum of the forces equals ma? When I teach vibrations, I tell students to throw in that inertia term, because then it's sum of the forces equals 0. Then knows all the forces. What's another way you can write A? Not EH, that'd be Canada. Okay, only a few people got it. Okay. What is it? dV dt. Or so acceleration is the first derivative of velocity. Yeah, it's the second derivative of position, which we call x double dot. If we sum the forces and we set them equal to 0 because we threw inertia in there, we got, and I'm going to say, it doesn't matter because I'll do this too, minus mx double dot minus kx equals 0, and we have this. Yep. This is where you apply your differential equations. What is a differential equations? All it is are sum of your forces. That's all a differential equation is looking at forces. That's it. The tricky part is solving them, right? This is what you have to classify. What is this? This is second order, homogeneous, constant coefficients, and you can go to a book or whatever, and the solution, or one solution, is written like that. You just find that in a differential equation book. You classify them, second order, constant coefficients, homogeneous. You go to the math book and you look up those rules, and it gives you that solution. They have that for thousands of differential equations. Okay?
Does vibrations involve a lot of differential equations?
It's only differential equations, pretty much. Yeah. That's pretty much all vibrations is. Yep.
A 0 or a diameter?
That's phi. That's your phase shift. So A is an amplitude. Omega is actually the frequency at which something's vibrating at, natural frequency. And this is your phase shift, meaning if you plotted like, not quite, but you know how like a sine wave can do this?
Mm-hmm.
Well, it might actually start here on the sine wave.
Yeah.
That's kind of what that is.
Really consistent.
What's that?
Your sine wave really consistent.
Yeah, no, actually, that's impressive. I can't believe I actually did that.
What course numbers, vibration?
Mech 412.
Forward?
Yep. 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 So,
Nobody will be teaching that next semester.
no, but if there is an interest, and there's only like a handful of people, I can do a directed study.
You would.
It would be an independent study, and I just say, here's the work, do it. Sure. Yep. Don't matter to me. It's actually, so what we do is we do this first. Where is it? We do that problem to make sure you understand how to do that. Then we add a damper in there. And then we add a force applied to it. Then we apply, there's tricks and techniques. If like the force is harmonic, like wind is usually harmonic, and there's a shortcut for that. And I'll show you different uniques of how to solve for the damper to get your velocity to dampen out. So, yep, it would be the exact course, and I would say, here's all the work, give me the work, here's your test. Sure.
How challenging is it?
We gotta figure it out.
It's I would say it's mostly math. There's a lot of math involved. And then I'll do probably an experiments with you.
I thought
I would really do
Yeah.
it so they get better.
So it's pretty much differential equations, yeah. So if there is an interest, talk amongst each other and let me know. And I would just do it. I don't need to get paid for it.
Wheatstone Bridge in the mechanical system.
I do not know how to do it.
Well, we're screwed.
That's what we're trying to do.
That's what you're doing? Okay.
We're really screwed.
Um,
Long graph of it, but that's a sponge, yeah.
So just a little side note, but I hope it now helps a little bit about differential equations, what they are, where they come from. The tricky part is then solving them. And that's what differential equations really is for, is you know how to classify them, how do we solve them? So this is the first year mechatronics.
That's electromechanical.
Mech 128?
Yeah, we long graph.
Right, we covered it in,
With Kanina? The Mech 128?
no, with,
Robin? McCullen? Oh, okay. I didn't know that.
Yeah, 128 for Wheatstone was stuff.
When I taught it, it was mostly, we did electrical first, right? And then we did, I don't know what he did, but then we did electrical, then we did mechanical systems, and then we did enough to get you through. But yeah, now it's, I don't know what it is now. I don't know. Yeah. Okay.
we spent like 2 weeks on that stuff.
I remember doing Wheatstone bridges. We did that. I know we did Wheatstone bridges because that was the biggest thing that students had hard issues with. Yeah. Okay. Okay, so let's just write this again. Or you already have it, but I'm kind of sidetracked there for a second. Actually, that's cool too, because one of the homework problems in vibrations is, do you go fast or slow over bumps? And you validate that to go faster. You don't get, and that's actually proof. So just
It
FYI.
allows the shocks to do their job.
Yep.
Otherwise, you just end up bouncing home.
Yep. Yep.
My uncle said it just so he didn't spill the martini.
As he looks at his clock, yep, it's just about time for mine.
All right.
No,
Let's just kind of quickly talk about where this equation kind of comes from. Okay. Let's see here. So, if you take a cannonball, it has a diameter d, and if this is moving to the right, or your left, okay, it's got to do what to this air in front? It's got to push out, it's got to actually push out the amount of volume, so this is meters cubed, say in 1 second, say this thing moves this far in 1 second or whatever, it's got to actually move what? That much amount of volume out, right? Okay, does that kind of make sense? Okay, and then how do you find mass flow rate? Yep, or it's just rho times V dot. So we have this cannonball, it's moving in air, and say, for example, 1 second, it moves so far, but it's got to move that whole amount of volume of air out, and then it gets replaced in the back end. But it's got to somehow move that. Okay, mass flow rate, which is density times the volumetric flow rate. Last chapter, we knew that if you had flow shooting at you or flow going out, what was the general equation of force for fluid? M dot times the right side of that Newton's second law was summation of m dot times v, in and then out. So the general idea is your mass flow rate times v. So let's just plug in what we have. We have m dot, which is rho a v times v. This is in,
So it can just be v squared at that point.
it is. That is in that equation already, right? Well, what is 1/2 in CD? Those are just constants. So when they did these experiments, they started with this equation and realized it didn't work. But they were finding that different shapes were kind of consistent. So this 1/2 times CD, all it is just a correction factor for different shapes. Okay? And the idea comes from a cannonball and understanding, okay, it has got to somehow displace that much of volume per time. And we know from that standard force that's kind of that. All right? So this is kind of briefly where that 1/2 rho v squared CD8 kind of comes from. Okay, it's kind of cool. It's right in the stuff you've been doing. You just didn't realize that.
Very familiar with the Free Nation of Celestial Space, the guy that claimed, he claimed all the space, or all the, basically the known universe outside of the Earth as his own nation, then waited for the Earth to move out of the volume that it occupied, and claimed that too. Like in the 80s sometime, but
No, I didn't hear that.
Still going.
Oh boy. Oh, that's crazy. I did not hear that. Okay, let's look at drag and lift. And we're going to draw an airfoil. Oh, that's pretty.
That's why it's NASA for trespassing and everything.
Really?
Yeah, it's serious, like,
There's some weird people in this world.
the player goes.
I never looked into the guy that was gonna shoot his rocket. That was a steam powered rocket. Never actually got that.
Approved?
Well, he was gonna do it from public. He was gonna do it from public land, but then,
Oh.
like the state of Utah accepted it and said no, you can't do that. So because he tried to flat Earth somebody with property in Utah said, oh yeah, you can do it from ours, because he was gonna rocket himself up into the stratosphere
Uh-huh.
and take pictures to make sure that the Earth was flat. So I don't know if he ever actually was able to.
Inconclusive, so the game, no new evidence. And then everybody's offering to take him for rides and jets and everything, it's like, no.
Oh, man. All right, so here's an airfoil, which is part of the wing. And this is right up Will's alley, right? As this is moving, say, this way, it creates drag and lift, okay? So what we talk about drag and lift acts up, drag acts to the x direction. So lift is always in the y direction, drag is always in the x direction, okay? As you shoot around this, let me look here, let me draw this sketch. Oops. This is kind of roughly, this black dotted, what the pressure distribution would look like if we did a contour map, okay? it would be higher at the bottom. And the reason because it's higher at the bottom is because of the shape. And that's actually how we get the lift, because you have higher pressure pushing on the bottom compared to lower, okay? And what we can do is everywhere we draw these lines perpendicular to the surface. Anybody, and they're pressure, right? Pressure acts perpendicular to the surface, normal. So those are pressure. And I'll do one up front. Then you also have these forces that are on the surface, which are tangent what happened there? Tau is fine. So the black lines are pressure, and the parallel ones are shear, which you kind of know these from strengths or machine design, right? But those are for solids. This is for fluid now. You still get shear forces and you still get pressure forces. So if you actually looked at the x directions, which is your drag force, sorry. Thank you.
That's what we got. There's the last night. We didn't get that far, I guess. We can park today and pick it up on the hill. Watch it a couple times. How's it working? Should be good. What's your expectation? We're looking at 400 yards. Maybe put some weight on it.
So don't worry about these. This is just for you to know. The drag force is the x direction. It's only the forces in the x. So what you have to do is you have to break out every one of these little forces around the whole thing and only look at the x directions. Okay? And you'll find that that term is actually 1/2 rho v squared CD times A. Okay? This you learn if you take an aerodynamics course. You actually dive deep into that. Okay? The y direction, which is lift, is basically your y component forces.
And doesn't offer an aerodynamics course, does it?
Nope, nope. That's one that I could teach, but Inder did want it, but eventually we just kind of didn't do it. But you could take it at Clarkson.
We're not really taking out of those.
If you're getting into the fluids, turbines, airplane stuff like this, yeah, this is right up your alley. Yep. So for you guys, as long as you understand that the bottom line is drag is only in the x, lift is in the y, those two equations, that's what you need to know. Okay? If you're going to start designing wings and actually making the new next airplane, yeah, you take an aerodynamics course and you learn this stuff. But don't worry about that. Okay? I just wanted to show you kind of briefly where that part is. For that project I've been talking about, is I'm going to have you set up a homemade lift drag setup. Okay? And we're going to use the one in there, but then we're going to take that one out and replace it with weights, with strings. and show you how you can do a mechanical force balance and still get the same results. And in order to get lift, where does the string need to come from, do you think? You want to hook up a string, you want to measure lift. That would be bottom or the top, right? Okay, drag would be either the front or the back. Okay, so we would probably do either probably the top because of our wind tunnel for lift, and the very back for drag. Okay, so if we can measure forces this way, drag, we can figure out how to do this, would be lift. Okay, so that's as long as you understand how to do that, that's actually the best thing for you. Okay. All right, making good progress.
Do we want control from like the top and the bottom, or would you just
Doesn't matter, because as long as you
start with the control?
start with as long as you know if it goes up or down, you could figure out that lift. For example, I have a scale, just a regular scale. If you build a wing and you mount it and you put it on the scale and you turn a fan on and you blow it, if the scale gets negative or negative values, you get lift, right? Or, yeah, because it's lighter. So that's how you could do it. Or if it goes positive, it pushes down, okay? I used to do that, and I could show you that quickly just to give you an idea. I did that last year as a project. They built a little wing out of paper, and we put it on there, and we did a competition. But now we have the wind tunnel, and we have printers. I'd rather have you design something and print it. Then it's a lot better shape, so.
Just one string from the top, or it's loose, that's what I'm thinking.
Oh, we would make sure it wouldn't be loose. Yeah, it would have to be attached. Yep, somehow. Yep, or some sort of mechanical arm that goes up and down. Yep. All right. So far, so good. Kind of random stuff, but it's good. So let's talk about. We talked about drag. So in your homework problems, a lot of is. I think for example, one of the homework problems, there's a stop sign, and there's wind blowing on it. Find the drag force. Okay, or a moment. It might be even a moment too. It might be. I don't know. But you can, right? I think actually that is probably. Actually, no. There's a truck with wind blowing on the side, and it wants you to find, I think, the height or the width of the truck so it doesn't tip over. But that uses drag. Okay. There's other parts of the homework that deal with boundary layer. And I need to put. So let's talk about, I think actually number 1 is boundary layer. Hey, what? Talk about iPhones dying. This is like, as soon as they announced Surface Pro 6, this battery's now been crapping. I don't know if I can or not. Probably not.
I thought they put the screen on. It's just a whole piece of it. Put the screen on.
Oh, the battery is in there?
Oh, I would assume,
I guess that's gonna work.
unless there's screws on that.
Okay, boundary layer. Here is a flat plate. Wow, that is not a flat plate. I don't know why I always make it harder for you. Purple flat plate. And we have flow left here. Flow is going to go over this flat plate. Give me an idea what's going to happen near the surface in the front and the back of this plate. It will eventually, yep, eventually. Might not, because it might just be nice and fine, but it could. If there was a little bump in here, probably, most likely will. What's going to happen is you're going to get a boundary layer that grows. Meaning, if we plotted velocity, heat transfer, you probably did this. You looked at this, right? Yep. Because you need to know what type of flow you are and where your boundary layers are. What's that? Yep, heat transfer did this. Anywhere from the red down, the velocity is 0 at the surface and increases to pretty much your U-stream velocity or whatever velocity is upstream at the above the red. Okay? And what happens is it first touches this, the velocity to the surface is 0. It sticks. And then as it keeps moving down, all this velocity is 0, and it's grabbing more of the above molecules and slowing those down. Okay, that's why this grows to the right. Okay? All right, does that make sense? So any object, you're going to get this boundary layer. Now, it's not this dramatic. Sometimes it's really, 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 really small. Okay? But it goes, remember when I was talking about my project that I did for my PhD? I had those inlets on the belly of the plane. I had to make sure that, and you don't have to draw this, but my shape was outside of the boundary layer to capture free stream air. Because if it was in here, I wouldn't be getting, it would be a mixture of whatever's in here, and that's not good. You don't want to do that, okay? So boundary layer grows as the surface gets longer. And sometimes, and I'll redraw this down here, sometimes you have nice flow, and then it starts becoming too large, and it kind of just slows right down, and then all of a sudden you get these reverse flows. Okay, so this would be laminar flow, and this is turbulent. And that all depends on how fast this air is moving, how long the surface is, and there's examples of how you determine kind of, and we'll go through that. Yeah, it wasn't, the boundary layer is not very far. The other thing we had to worry about was location right and left, because if you have an inlet straight ahead of you, you don't want to be measuring in that. So you have to know that wake region of that. So we had to figure out, we had to try new spots, and we found one that was, we know, okay, that actually worked right. Yeah, on the belly, yep. Yeah, we compared it to 2 or 3 that were in the front of the plane, way up top, because you can do it in the top too. And we compared our measurements, and they were comparable. But when we moved it, it wasn't even getting close because something upstream was interfering with our measurements. So boundary layer creates it. Okay, it's created. It gets bigger. You could have a laminar. You could have actually here. It's called the transition. And then you have turbulent. So I'll give you these equations here. Oh, draw this on your sketch. This distance is delta up here, the boundary layer. The boundary layer thickness is called delta. I might as well keep that there. And this is how they write it in books. This is 10 to the third, less than Reynolds number, less than 10 to the 6. This is REX, greater than 10 to the 6. The students in heat transfer, did you have those? Remember? Okay. Well, you had to find the Reynolds number because you had to determine if it was turbulent or laminar, right? and then use the specific heat transfer equations for that.
What's the purpose of the substrate on the Reynolds number? Is it-
X, just meaning this is direction of X. Yep.
Okay.
Yep. So if you notice, it's due to the fluid properties, so density, viscosity, how fast you're moving, and the position you are. There's going to be times where maybe this is all laminar because it's not moving as fast, for example. Or maybe the first section is laminar, then all of a sudden it becomes turbulent, and you get these circulations created. Okay. The first homework on your problem has you plot. I want you to plot a kayak, or not a kayak, the boundary layer underneath the kayak. So you have to figure out, okay, is it laminar at this case? Is it turbulent in this case? And figure out what your delta is. And they do, it's weird, they do delta over x. That x actually needs to be multiplied on the right. But this is how they write them in all the fluids books. It's weird why they do that, but they just do it. Okay? So in that case, you have three cases, laminar, transition, turbulent, but we ignore this because this is the hardest to design for or to even study. Okay? We either pick one or the other. All right? You have two cases here. Cases. So in a programming aspect, what does that mean? You know what I mean? If statements. Yes, they're if statements. That's what so if Reynolds number is less than 10 to the 6, use this equation for delta. Else if, or else, use that. Okay? Want me to help you with that? Just to give you an idea of the MATLAB code?
Yep.
Okay. Thank you for... So, let's make X. And I don't know the dimensions of that kayak. Actually, I can find out. And it's pretty much all I'm going to cover today anyway, so I've given you a lot of information. We'll continue this on Tuesday. All right, so here is a, when is it due? '30th. So I figured I would give you time. We'll finish this up. We have lots of time Tuesday next week and Thursday. And then most likely on that Tuesday the 30th, you could probably wrap up some stuff. Then I'll give you those little projects, hands-on stuff that I probably want you to do for a couple days. Okay? Then we'll get back into here and do more lecture stuff. Okay? All right. So here's the kayak. So I'll give you the speed, 3.5 miles per hour. I'll give you the temperature, so you could find density, you can find viscosity. What's that? Canoe. Oh, sorry, it's a canoe. Okay. I like it, Will. The first question is the boundary layer in the canoe bottom, laminar, or turbulent? Okay, so I would say for that one, you're pretty much going to solve it in the plot. Okay, so what I want you to do is create a code that plots it, but you need to check, okay, is it laminar or turbulent? So it's 20 feet. So X is going to go 0 to 1 to 20. Okay, now what do we need? We need to define density, mu, v. Say that again? Those are colons, not semicolons. Then under your solution, you're going to find a Reynolds number, which is rho v x divided by mu. What's that? Well, I'm figuring on helping. It's for the good cause. See where I'm getting at? You're going to need to know. Okay.
For sure.
Yep. So you calculate Reynolds number. For each Reynolds number, you need to check, right? So, for I equal 1, the length of REX. What does that mean?
Gonna look at the Reynolds number to see what its number is.
Yes, so we will get to that. This is just saying that it's going to start with 1 and it's going to go as many times as this matrix is. So what we need to do is we could say if REX of I is what? This is less than 10 to the 6. Delta of I equals blah, 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 blah. Else, Reynolds number, oh no, we don't even need to do that. You just say delta is the turbulent one. So this would be the laminar case. This is the turbulent. Let me actually write the laminar one in, which was what? 5.0, and I'm going to do it like this. REX to the raised to the negative 1/2, right? Or you can do divide, it's up to you.
What's that before?
Oh, multiplication. Yeah, make sure you put that in there, right? MATLAB throws a fit if you don't put the asterisk. Yep. So 5 times REX parenthesis I raised to the negative 1/2. You don't have to do that. You could do divide to the that you can. I brought it up to the surface. I made it negative 1/2. Okay. Why did I need the parenthesis I here? Because I want to figure out what the delta is for that specific Reynolds number, not all the Reynolds numbers. Okay. Then you do the same thing for that, and then how many end statements do we need? 1, 2. And say you're just typing this and it's unorganized, just highlight this section and Control I. It'll format for you. Okay. Dynamic students is double, double, double for loops. You just had to do for loop, and now you're doing another for loop. So for loops are good. Questions on that? Okay, let's stop here. We'll continue Thursday, and we'll go from there. If I find that you need that Tuesday to work and we can start, that's fine. I'm okay. Because there is this MATLAB, and then the differential equation MATLAB. I want you to keep working on ANSYS or Inventor. So, yeah, we're still good. We're still good. Okay, thank you.